As we have discussed about the mathematical induction concept, let us see the example now. First example is for all n greater than or equal to 1, we need to prove that this expression, or you can say this is a series of squares of natural number added. This is equal to n plus 1 to n plus 1 by 6. So how we are going to do this? Let the given statement this be Pn, we assume it to be Pn, and this Pn is nothing but the equation or the expression being given. Let us try it for n equal to 1. This is the basic step. Let us put 1 here, so 1 square. Let us put 1, 1, 1 here, and you find it out that the answer would be 1. So the left hand side and right hand side become 1 for n equal to 1. Then next is the inductive hypothesis or induction step. We assume that pk is true for, say, some positive integer k. So 1 square, 2 square till k square is equal to k plus 1 to k plus 1 by 6. We assume it to be true for k. What about k plus 1? So this is the k. We are just adding one more element, that is k plus 1, and the same stuff we have to add here. Okay, this is the k1 and this is the k plus 1. This we already know here. This we already know what is this. It is equal to k plus 1 to k plus 1 by 6 through 1. This equation 1. Let us place it here, and when we solve it, or you see this is 2k square plus 7k plus 6 after solving this, and let me factorize it for you. So this is 2k square plus 7 can be taken as 3 and 4, so 4k plus 3k plus 6. Okay, this can be written like this. So this will be equal to 2k, k plus 2, and this will be equal to 3k plus 2. So the factorized value will be 2k plus 3 and k plus 2. Okay. This k, 2k plus 3 can be written as 2k plus 2 plus 1, this is like this. This k plus 2 can be written as k plus 1 plus 1. So essentially what we have done, we have tried to prove that this k, this for k, if it is valid, for k plus 1 also it is valid. So you want to place k plus 1 and k plus in terms of k plus 1. So this is also true. When it was true for k, it has we have already showed that it is already also true for k plus 1. So this is how we do it. And this, okay. So this is the principal mathematical induction of principle. Let us take one more example. We need to prove that 2 to the power n greater than n for all positive integers n. This is our Pn. So Pn is 2 to the power n greater than n, and we need to understand that it is for all positive integers. Let us make it for n equal to 1. For n equal to 1, what will be the answer? Let us place 1 here. So 2 to the power 1 is greater than 1. Yeah, 2 is greater than 1. This is true. Hence, this P1 is holds. Let us assume that Pk is true for any positive integer k. That means we assume that it is true for some k. So 2 to the power k greater than k, we assume it to be. Let us apply it for pk plus 1, means the next member which is coming after k. What we can do is, let us multiply this expression number 1 by 2 on the both sides. So we are multiplying 2 and 2. What you get here, 2 to the power k is 2 to the power k plus 1. You know that a to the power m, a to the power n is equal to a to the power m plus n. So this is 2 to the power k plus 1, which is greater than 2k, because we have multiplied both sides. 2k is what? 2k is k plus 1, k plus k. 2k is k plus k, but we assume and we know that k plus k is greater than k plus 1. What I mean to say, take any value k, say 10. So 10 plus 10 will be always equal to 10 plus 1. That is 20 will be always greater than 11. So k plus k will always be greater than k plus 1. So let us replace this 2k and k plus k by k plus 1. So ultimately what we got, 2 to the power k plus 1 is greater than k plus 1. And this is what we wanted. We started with k and we got k plus 1. Next is the example 3. So for n which is greater than or equal to 1, we have to prove this. How are you going to get this? Let us see. So this is actually 1 by 1.2, 2.3. That means this is if this is n, this is equal to n plus 1. So 1 by n plus 1. This is equal to, if you sum this series till this last member, we are going to get n by n plus 1. So Pn is the same expression which you see here. What about P1? Place n equal to 1. So this is 1, this is 1, 1, 1. This is nothing but 1 by 1.2, and this is 1 by 1 plus 1, that is 2. So both the sides you get half. Half is equal to half. So for n equal to 1, this is true. Now let us assume pk means for any k, this pk to be true. What you get here is 1 by 1.2 plus 1 by 2.3, 1 by 3.4 till 1 by k plus 1 is equal to k by k plus 1. Please observe this equation, because we are going to use k by k plus 1 in place of this. Now let us write the pk plus 1 version of this expression. This is okay, we are just adding k plus 1 member. And as I said earlier, that we are going to use k by k plus 1 for this expression or this series. So we are using k by k plus 1 for exactly this, from 1. And now we need to solve this, and when we solve this, we finally find out this k plus 1 by k plus 2, that is k plus 1 by k plus 1 plus 1. So this is true. This was actually k by k plus 1 where we started. Now this is k plus 1 and k plus 1 plus 1. So this is true for wherever this pk we assume to be true, it will be true for pk plus 1 also. The next is, for every positive integer n, we have to prove that 7 to the power n minus 3 to the power n, it is divisible by 4. So what we can do here is, please understand that if this is divisible by 4, this is divisible by 4, let us check it for value equal to 1. So Pn is this expression or this statement, you can say. P1 you have to place n equal to 1, so n equal to 1, 7 to the power 1 minus 3 to the power 1, which is actually 4, and which is divisible by 4. So for n equal to 1, this holds. What about pk? Any k value you take. So this will be equal to pk is equal to 7 to the power k minus 3 to the power k is divisible by 4. So what you get? This is equal to, say, 4 into some value. You can take any value. Why I am saying this? Because if you say that 8 is divisible by 4, so actually you are writing 4 into 2. When you say 16 is divisible by 4, you are writing actually 4 into 4. So you are placing 4 and some natural number you are placing here. So what you can do here is, you can express this division in the form of expression, in the form of equality. That is 7 to the power k minus 3 to the power k is equal to 4d, where d can be any natural number. And now we wish to prove that this pk plus 1 is true whenever pk is true. So we assume it to be true. Let us take the k plus 1. So for every k you place k plus 1. So 7 to the power k plus 1 minus 3 to the power k plus 1. And what we are doing here is, please understand, this is very important step. We are adding 7 into 3 to the power k, and we are subtracting it. So we are adding it, we are subtracting it. Same value. This value we are not touching. Only these two values we are adding and subtracting. Why we are doing it? Why we are doing this? Because we know we have to get somewhere this 4d. So you can get this 4d if you can get this 7 to the power k minus 3 to the power k. If you take 7 common from here, this is exactly what? 7 to the power k into 7 to the 7. 7 to the power k plus 1 is nothing but 7 to the power k into 7 to the power 1. So you take 7 common, and 7 to the power k will remain and 3 to the power k will remain. And in the similar fashion, this has happened. Now take 3 to the power k common here. This is again 3 to the power k into 3 to the power 1. So you are taking 3 to the power k common. Inside this, you get this and you get this. This is what? This is 4d already. So just place 4d. And this is what? 7 minus 3 is 4. So you get 4 here. And now you can take 4 common from both the terms. So you are taking 4 common. So this is equal to 7d plus 3 to the power k. So ultimately you got 4. Whatever be inside, we are not worried about this, but it has a 4 as a number, a 4 as a multiple. So now we find and we presume now that this expression or this equation also is divisible by 4. So pk plus 1 true is true for all pk you think and you try for. So this is the principle of mathematical induction we have just applied to prove that this is actually a multiple of 4. So we stop for now and we'll be taking next in the next discussion. Thank you so much.